All righty. So we can go ahead and get started. So today we are going to finish up the math review by discussing vectors. So last time we went over trigonometry. And with trigonometry, we saw that there's a few important relationships that can be used to determine unknown information about right triangles. So what we saw from trig was that the first big one is the Pythagorean theorem. A squared plus b squared equals c squared. Right, so for some right triangle with side length a, b, and c, where c is the hypotenuse, that is the longest side of the right triangle, and with some angle theta, a squared plus b squared equals c squared, that's Pythagorean theorem. That's one big relationship. The next one is actually a set of three relationships, and those three are accounted for in the acronym Sohcahtoa. And basically, Sohcahtoa, as I said, stands for three relationships, and those relate the angle theta to the different sides. And so, for instance, this means sine of theta is the opposite side. And so in this particular example, the side opposite to theta is the b side over the hypotenuse of c. Cosine theta is the adjacent side, which for this particular example is a. And tangent theta is the opposite side over the adjacent side. So Sohcahtoa, it's a set of three relationships. It allows you to relate one of the angles in a triangle to two of the sides, depending on what information you know. Maybe you're looking for the angle, maybe you're looking for one of the sides, it depends. And of course, the last relationship is that the sum of the three angles, so theta plus phi plus the right angle of 90 degrees, because all of our triangles are going to be right triangles, always adds up to 180 degrees. So this basically allows you to find the third angle of a triangle, given you know the other two. And so these three relationships are everything you need to be able to, given a right triangle, solve for any information you need. Now, this is important for what we're doing today, which is vectors. So with vectors, what we saw in first semester physics, hopefully, is that a lot of physics makes use of this thing, this abstract concept that we call vectors. And it's kind of like a more advanced form of regular math. So the math we know that we learned since we were a child, adding numbers, multiplying numbers, things like this, is the math of what's called a scalar. Scalar just means numbers. Mathematicians have to come up with fancy terminology, and they group things very deliberately. And so instead of calling them numbers, this thing that we're used to as numbers, they call them scalars. And then there's something which is more advanced than a scalar, which they call a vector. And what this is basically like a number, but instead of it being something with a magnitude, which is what a number is, 5, it's how much, it's the size, the length, the speed, 10 meters, that's a scalar. It's how much, how far did it go? A vector gives you two pieces of information. It's still one thing, which we call a vector, but built in that one thing are two different pieces of information. Firstly, the magnitude, but also a direction. And so you'll have things like, as I said, the speed of a car, 35 miles per hour. That's how fast it was going. But then you can have something called the velocity of a car. And usually in our everyday terminology, speed and velocity mean the same thing. It's just two different words. But if we're going to be correct in terms of physics or engineering, speed and velocity are different. The velocity includes the speed, but it also includes something else, and that is in which direction were you traveling at that speed. So a vector contains both a magnitude, which is the size or the amount of whatever this vector is, and a direction. So not everything is a vector. Temperature, for instance, is not a vector. When you say how hot is it outside, or someone says what's the temperature of that of the bread you're baking, well, you say the oven's at 350 degrees. You don't see it's at 350 degrees north of west or something weird like that. Temperature is a scalar. It's just a magnitude. Velocity is a vector. You can say how fast something moves and in which direction it's moving. And we usually write a vector. Let's say we have vector A. And the general thing is to put a little arrow over it, since I can't write in bold face like a textbook can. You write a little arrow and that says this thing is a vector. And one way of saying it is the magnitude of A, and magnitude is represented by like absolute value symbols. And then an at symbol, some direction theta, So you can have something like, oh, it's 10 meters at an angle of 30 degrees north of west, or north of east, let's say. So this is a way of writing a vector. We have two pieces of information. How far, the magnitude, it went 10 meters. But it went 10 meters in which direction? This particular thing went in this specific direction. And if we want to draw it out and represent it graphically, we would have the east over here and north over here. And we would write any vector. We would draw a vector as an arrow that sticks from the origin and goes out a certain length, which is represented by the magnitude, and points in a direction given by the direction. So in this case, it would be something like this. There's that. There's our vector. It's vector A. It's got a length of 10 meters, or it's a scaled length of 10 meters. And this angle is 30 degrees. And so that's what a vector is, or at least that's two different ways of writing a vector, graphically and analytically. That is with numbers and letters and stuff. Now, what do we do with vectors? Vectors allow us to solve more interesting problems in a more efficient way, as long as we know what we're doing. And it turns out that the math of vectors is different than the math of numbers. With numbers, if I say add 3 plus 5, well, 3 plus 5 is 8. Everybody knows that. You get the answer. You just do it. There's no fancy technique. But with vectors, if I say you have vector A and you have vector B, add vectors A and B together to get some new vector C. What do? You have two things here for each vector, a magnitude and a direction. So if you're adding two vectors, do you add the magnitudes and add the directions? Do you add the magnitudes but not the directions? But then what do? You have two different directions. So do you say, how do you mess with this? And it turns out that the mathematicians worked on this and they said, look, you just can't do it. If you have two vectors which point in different directions, there's no way of adding them. It's meaningless to add them. The problem is, in terms of physics, it does make sense to add them, because we can ask the question. Let's say you walk out of your house 10 meters at an angle of 30 degrees north of east. Then from there, you walk an extra 20 meters due north. And the question is, if you want to go from, let's say, your wife or your husband or whatever in the house, wants to meet up with you and they want to walk straight to where you ended up, in which direction and how far should they walk? Right? So if I were to graphically show this, well, there's A, and then from there you went up 20 meters. So that's B. And so someone wants to meet up with you, they'd walk straight this way. And the question is, how far should they walk and what should this direction be? That's a meaningful question. And obviously, if we think about it, the way to answer the question is to add the vectors A and B together to get this new vector C. So we have a conflict. Math says you can't do it. Physics says we should be able to do it because I can think of problems whose answers are doing it. And so smart people thought about it and they came up with a way to do it. And it's a trick. They say, you're right, we can't add two vectors if they're in different directions, but what we can do is we can say, look, take the first vector A. So if this is vector A, I know its length is 10, and I know that the angle this thing makes with the horizontal here is 30 degrees, right? Well, instead of thinking about the vector like that, I could think about it slightly differently. I could say, okay, how much of this vector points purely in the x direction? Well, that would be this much. It goes out all the way to here. And then how much of the vector points in the y direction? Well, that would be this much. So this vector A, which is 10 meters at an angle of 30 degrees, can be comprised of two different things. One, I walk a certain amount in the x direction and a certain amount in the y direction, and I get to the same place. And so what I can do is I could take this vector A and break it into its two components, the x component and the y component. Okay, let's say I can do it. I'll come up with a way to do it. Let's not worry about the way to do it yet. Let's say I can do it. Then I do the same for B. I say, well, with vector B, I could do the same thing. How much of B points in the x direction? How much of B points in the y direction? And so then I'd have some x component of B and some some y component of B as well. Okay, so say I've done it. I've come up with the way to do it and I have the numbers. Now what I can do is I could say, look, AX and BX point in the x direction. So they're in the same direction. So those two things I can add together, AX and BX, because I'm not violating math's rules. Math says if they point in different directions, I can't add, but the same direction, there's no problem. So I can add them together to get some new x component of C. And of course, likewise, I could do it with y. I could take the y component of A and the y component of B, and that'll give me some new y component, which I'll call C. Okay, so this is kind of most of the way there. All I have left to do is come up with a way of combining these new x and y components of my new C thing here to form one vector out of it. And we know how to do it. Because if you notice what this is, if I were to draw this out, this is nothing more than Cx goes some amount this way, Cy goes some amount this way. And what I'm looking for is this thing here, which is if I were to start from the beginning and go straight to the end, what would be this length? That thing I'm going to call the magnitude of C. And the direction, this angle here, that'll be called the direction of C. This side is Cx, this side is Cy. I know Cx and Cy. They're numbers. Well, I know how to do this. This is trigonometry. All I did was draw a right triangle. Wednesday, we saw, given a right triangle, if I know two of the sides, I could get the third. That's Pythagorean theorem. And so Pythagorean theorem would say, if I want the magnitude of C, Well, I know c squared is a squared plus b squared. So if I want c, well, it's the square root of a squared. Well, a, I'm calling it the x component of c. Plus b squared, well, b, I'm calling it the y component of c. It's just a different name for the same thing. The two sides of the triangle, square them, add them together, take the square root, that gives you the hypotenuse. The hypotenuse is called the magnitude. So now I have the magnitude of my vector. What about the direction? Well, again, this is just a trig problem. I'm looking for theta. I know cy, which is the opposite side, and I know cx, which is the adjacent side. And Sohcahtoa tells me tangent of theta is the opposite side over the adjacent side, which for us is cy over cx. So theta then is the inverse tangent of cy over cx. And now we have our two big formulas for calculating the magnitude and direction of a vector. If I happen to know a vector's x and y components, how did I get them? Don't worry about it. I have them. I'm told the x component of the vector is 3, the y component of the vector is 4. The question is, what's the magnitude of the vector and its direction? How do I calculate it? These equations tell me. Where did they come from? It's purely trigonometry. It's what we did Wednesday. I make a right triangle. The hypotenuse is the line I'm calling the magnitude, and the direction is just one of the angles in the triangle. If I want the hypotenuse, I use the Pythagorean theorem. In this case, a squared and b squared have new names because a represents the x component of the vector and b represents the y component. And for theta, I'm using one of Sohcahtoa. Which one do I use? The one that I know the information about. I know the opposite side and I know the adjacent side. So I'm using tangent. So it's not some new equation. It doesn't come from some fancy place. It's purely the same thing from trigonometry, only now it represents something slightly different. It represents vectors. Now that's the theory. Let's do an example where we see how to actually do this, okay? Because first of all, I didn't tell you how to get the components yet. So let's say we have this question. The question is, vector A is 10 meters at an angle of 30 degrees north of east. Vector B is 20 meters at an angle of, let's say, 60 degrees west of north. Okay. And what I'd like to do is calculate A plus B equals C. Okay, so this is purely an abstract question. There's no physics to it. It's purely math. I have two vectors. Give me the sum of the two vectors. It represents something physically, but I don't care what it represents. How do I do it mathematically? Well, let's look at vector A first. Here's the coordinate system. Vector A is an arrow. It goes out 10 meters and it points at this 30 degrees north of east. So when I see 30 degrees north of east, what it tells me is start east and then go 30 degrees north of that. So here's the east. So I'd go up 30 degrees. So here's my vector A. Now, what do I want to do? What I want to do is make a right triangle out of this guy so that I could get his components. I know this is length 10. So say, okay, let's have a vertical side. And the vertical side, I'll call AY, the Y component. And we'll have a horizontal side. That side, I'll call it AX. And then lastly, I'll call this angle here theta, but I know what theta is 30 degrees. I'm giving it in the problem. And now this is purely a trig problem. The question is calculate AX and AY. So how do I do that? I'm given a triangle. Here's my triangle. Hypotenuse is 10. Here's my X, here's my Y. This is 30 degrees. Well, I have Sohcahtoa. Let's look for X first. So I'm looking for X. In this case, X is the side adjacent to the angle. And from Sohcahtoa, adjacent goes with cosine. Sohcahtoa, the middle one. So I know cosine of theta is the adjacent side, which is X, divided by the hypotenuse, which is 10. Perfect. Of course, I know theta. Let me go ahead and just plug theta in as 30 degrees here. And now all I have to do is solve this little equation for X, which is easy. Bring the 10 over to the other side, and we have X is equal to 10 cosine 30. And there we go. We've done it. What is the X component of this vector? 10 cosine 30. Which for us, if I plug this in my calculator, you should get 8.66. What about the Y component? Well, same thing. Here's a question.
Just asking. I was just asking, would you use the sign for that?
Yeah, so for Y, we would say the Y side is the side opposite to the angle. And Sohcahtoa says opposite goes with sine. So exactly, the Y piece would say sine of 30 is the opposite side, which is Y, over the hypotenuse, which is 10. And again, if I rearrange it, Y is 10 sine 30. Now, and so 10 sine 30, which is 5. Now be careful. In this case, the X component with cosine and the Y component with sine. But that's not always true. Okay, and in fact, when we do B, I think it may be the opposite. Depends on how I do the triangle. But don't memorize X component is always something cosine something, because it's not always that. Sometimes the X piece has sine in it instead of cosine. How do I know? You make the triangle, and then you use Sohcahtoa from the triangle. In this case, I look at X. X is the side adjacent. Because it's the adjacent side, that's why it's cosine. If I had some other triangle, and in that triangle, the X side was opposite, then the X would go with sine. But here it happens, X is cosine, Y is sine. It's an example. All right, so A is done. X and Y components finished for A. Let's do the same for B. Exactly the same process. Here's B. B says 20 meters, 60 degrees west of north. Okay, so I start north and I'm going to go 60 degrees west of it. So it's something like this. This is 20 meters. And I know this here is 60 degrees. So that's what B looks like. And again, I want to get the X and Y components. I want to find BX and BY. Same process. Make a triangle out of this. Now, notice, and I get this every semester. There's two ways I can draw a triangle here. First way is I can draw a line down here. And so there's my triangle. That's perfectly fine. The issue, which is why I'm not going to do it this way, is notice the angle given in the problem of 60 degrees is not in my triangle. It's on the other side. So then I'd have to know, oh, this angle is 30 degrees because 60 plus 30 gives me the full 90. Well, I don't like having to think. The less I have to think, the better off I am. So instead of doing this, make the triangle have the information built into it. So for me, my triangle will be this one here. There's the X side, and here's the Y side. Again, it's a right triangle, but this time the angle that's in the problem is now in my triangle. Perfect. The horizontal side is always called the X side. So that one's the X. The vertical side is the Y side. There's the Y. Now I do exactly the same process. Here's a triangle. It's drawn upside down from what I'm used to, but so what? There it is. I want to use Sohcahtoa for this triangle to get X first. So let's see, the angle of 60, X is the side opposite to that angle. Opposite goes with sine. So sine of theta, sine of 60, is the opposite side, X, over the hypotenuse, 20. So rearranging, X is 20 sine 60. So I get 20 sine 60, which is 17.32. However, we have to be very careful. I skipped over this in the last example with A because I didn't need it, but now I do need to worry about it here. Vectors or components of vectors can be positive or negative, depending on which direction they point. Notice vector B is pointing up and to the left. Now, when we think about vectors, one of the things you learn in physics is you have to separate independently horizontal stuff from vertical stuff, or X direction and Y direction. They're separate. So this vector points up and to the left, but if I'm looking in the X direction, the X component, all I care about is the leftwards or rightwards-ness. I don't care about up and down. So B points to the left here. To the left is negative. Left is negative. So my X component of B, since B points to the left, has to be a negative number. So I put a negative sign on it. Okay. Notice for A, I didn't do it, but that's because A pointed up and to the right. So in the X direction, to the right is positive. Right is positive, so I didn't have to make a negative. All right, what about the Y component? Well, the Y side is the side next to the angle, so it's adjacent, so that means cosine. Cosine of 60 is Y over 20. So Y is 20 cosine 60, which is 10. Is he positive or negative? Same thing. B, up and to the left. In the Y direction, he's upwards. Upwards means positive. Downwards is negative. So the Y component is positive. Even though the X is negative, that doesn't mean the Y has to be negative. They're different things. The Y is pointing upwards, so he's a positive number. And now, of course, I have the X and Y components of my B. And this is how you do components, or this is how I do it. Now, I may not always physically draw the triangle. Obviously, I have a lot of experience with this, and I'm very comfortable. So I could just look at the vector and do the components in my head. But until you get to that point, just draw the triangle and use the triangle. And the big thing is to worry about, is it positive or negative? There's two areas where people make mistakes. Firstly, do I use sine or cosine? And the only way to know that is to look at the triangle and to say the side I'm looking for, is that opposite or is it adjacent? Secondly, is it a positive or a negative component? And that is it pointing left or right or up and down? Okay, now I went through this rigmarole here just to show the formality of where this stuff comes from. It comes from Sohcahtoa. But when I actually do these problems, I don't do this work. I say the X component, X side is opposite signs, so I just write it out. I don't have to actually start here and then do the algebra. But that's because, like I said, I've done 1,000 of these problems. If you're comfortable with it, you don't have to start at this point to get to this. Feel free to just write the answer, or write, oh, it comes from sine, and then give me the number. If you're not comfortable yet, then do the algebra to get it. But I wanted to show that where this stuff comes from is not out of the blue. I'm not making it up. It's not some secret. It's just Sohcahtoa. And I use Sohcahtoa to get the answer. It's just that usually when we use Sohcahtoa, we're looking for the angle, theta. But in this case, we know the angle. What we're looking for is one of the sides. So we rearrange it to get the equation. So before I move on, any questions on calculating the components of a vector? Okay, now for question?
Yes. Can you scroll up to the question, to the actual question you asked?
Yeah. So it's a very generic question, but it is, here's vector A, magnitude of 10 and a direction of 30 degrees north of east. Some other vector B is a magnitude of 20 at an angle of 60 degrees west of north. Given these two vectors, add the two vectors together. That's what we're working on. And the process is first get components, use the components to get the components of C, take the components of C to get the magnitude and direction, your final vector. So what we've done so far is just the components. Now, in physics, of course, there'd be a story here. And I gave you an example. You walk out of your house a certain distance, then you turn and walk another distance. And the question is, how far from your starting point do you end up? Or you're swimming in a river, 10 meters per second, and you're going in this direction, but the current of the river is pulling you in this other direction with this speed. So if someone's looking at you in the water, how fast are you actually moving? Because your speed and the speed of the current add together and it moves you in a certain way. Okay, that's the fancy story that goes with physics. The math, what we're actually doing, the mechanics, is this. Vector A is this, vector B is this, add them together to get some new thing. So it's interesting that you have 1,000 different problems or stories in physics, but at their heart, this is all you're doing. It's just that you think about it differently, or I do at least. So we have our vector components. We have AX and AY, and then we have BX and BY. Now, why did I do it? Again, I can't just add the vectors because they happen to point in different directions. But now what I can do is I can say, look, CX is AX plus BX. That is to say, if I take the X component of A and the X component of B, since they're both in the X direction, I can add them together and get some new X component. So what is that going to be? 8.66 minus 17.32. Oh boy. Do I have, yeah. Let's see if I could do this. Uh-oh. Yeah, I don't have my calculator or my phone on me. If someone does, can someone please go ahead and calculate that out really quick? I guess it's negative 8.66. Probably. If someone could confirm that for me.
I got negative 8.66.
Yes, 8.
All right, good, perfect. And then CY, exactly the same thing, only with the Y components, AY plus BY. AY was 5, BY is 10, so I get 15 for the Y component of C. Come on. Why is it not updating for me? Let me stop sharing and reshare because it's not keeping up. Let me see really quick. All right, share. There we go. All right, can everybody see it now? The 15 is shown up.
Yes.
Perfect. All right. So now we have some new vector C, whose x component is minus 8.66 and whose y component is 15. Let's go ahead and draw it just to see what it looks like. If I were to draw this vector, how would I do it? I'd say, well, in the x direction, I go to the left 8 or 8.66. All right. So I go this much, 8.66, and then 15 in the y direction. So I go up 15. So this vector looks something like this. Okay, and I'll call that vector C. Now, what do I want to do? What I'd like to do is get the magnitude, which is how far do you have to walk, and the direction. In which direction do I walk? So what I want is this angle theta, and I want this side length here, C. That's what I want to do. How do I do it? Well, we just saw in the theory over here, way up here, that when I want to find the magnitude of a vector, if I know its x and y components, it's just a Pythagorean theorem. So magnitude of C is the square root of the x component of C squared plus the y component of C squared. So square root of minus 8.66, all of that squared. And remember, the negative is also squared there, and 15 squared. Okay, so I'd plug this in my calculator and I'd get some answer. That's the magnitude. The direction, how do I calculate the direction? Well, we saw again back with the Sohcahtoa stuff. If I want the direction, I use inverse tangent of the y component over the x component. So inverse tangent of the y, which is 15, over the x, which is minus 8.66. Okay, now, this is very important. So since I don't have a calculator, I'll ask somebody, can somebody please calculate that for me? Inverse tangent, make sure you're in degree mode. Inverse tangent of 15 over negative 8.66, and tell me what answer you get.
I got negative 60 degrees. Well, 60 degrees. I don't think anything could be negative degrees.
All right, so negative 60 degrees. That's what your calculator tells you, right?
Yeah.
Okay. Well, first of all, it can be a negative angle. There's nothing wrong with a negative angle. But let's see if it makes sense. And this is a very important thing in vectors. Unfortunately, we have to worry about this. Whatever the magnitude tells you, as long as you plugged it in correctly, the answer is perfectly fine, and you can always trust it. The direction, half the time, is wrong. Even though this equation is perfectly correct, and you plug everything into your calculator perfectly correctly, half the time you get an answer, it's going to be wrong. So let's see, is it wrong or not? How do I know if it's wrong? Well, this angle here, if it's right, then what should the vector look like? If I'm going to draw a vector that points down 60 degrees, well, that would be a vector that points down this way, where this is 60 degrees, right? A negative angle means it goes downwards that much. So the answer I get says the vector should look like this. But looking at the x and y components, I know it should actually look like that. So they don't match. Something weird happened. It definitely should look like this. My answer tells me it looks like the bottom one though. If they don't match, then you know this is wrong. How do I make it right? Very easy. Add 180 degrees to it. So The actual answer is 120. Every single time when you get an answer, a direction, look at the components. For me, the components say it's to the left and it's up. How much? I don't know, 100 degrees, 180 degrees, whatever. It's to the left and it's up. I look at my answer and it says -60. Well, that's down and to the right. Since they don't match, I know just add 180 and now it's right. If instead I look at my components and the components were positive 8.66 and -15, and that says go to the right 8 and down 15. So it's down and to the right. I look at the answer, I get -60, that's down and to the right. They match, so it's right. I don't have to mess with anything. Okay, so that's a warning. You have the correct equation, you plug it into your calculator perfectly correctly, and you're in the right degree mode. And still your calculator can give you a wrong answer. And the reason is simple if you think about it. Look at what we plugged into this calculator. Inverse tangent of 15 over -8.66. What's the difference between that and inverse tangent of -15 over 8.66? Well, to you, you know the difference because you know this 15 stands for something. It's how much in the y direction. And -8.66 is how much in the x direction. So the one on the left is upwards 15 and to the left 8. And the one on the right is downwards 15 and to the right 8. But to your calculator doesn't know the difference between 1 over -2 and -1 over 2. It's both -1/2. And so your calculator has no idea that these two things are supposed to be different. So it can only give you one answer. And so because of that, when you get an answer, it's possible that the calculator just gave you the wrong one. If it gave you the wrong one, you add 180. If it didn't give you the wrong one, then you leave the answer the way it is. And again, how do I know if it's wrong? I imagine these components in my head. The x piece, -8, means to the left, and the y piece, positive 15, means up. So up and to the left. The answer I got, -60, that's down and to the right. They're in opposite directions, so they don't match. Okay, another way this can happen is if you have 1/2 or -1 over -2. Well, 1 over 2 means up 1 to the right 2, so up and to the right. And -1 over -2 means to the downwards 1 and to the left 2, so it's down and to the left. So again, opposite directions. But your calculator would give you the same answer. So this is something every time you do a vector problem and you have to calculate direction before you box the answer, take an extra 5 or 10 seconds to either draw it out or in your mind, look at the components. Which direction will that arrow point? What does my answer say the arrow points? If they're in the same direction, then you're fine. And if they're not, then just add 180. You don't have to do anything more than that. And that's vectors. That's everything we're going to do with vectors. Now, obviously, in the actual class, when we have problems, the problems will have equations and stuff we're doing here. And so what we may do in the actual physics problem is we may have something like you have these electric charges arranged in some way, and they all push on each other because of the electric force. And I want to know what's the total force felt on this one charge. How do I do it? Well, I add how much force this guy pushes plus how much force this guy pushes. So I'm adding a bunch of forces together. That means I'm adding a bunch of vectors together. So first thing I do is figure out how much force is on each vector, or how much force is due to each charge. That's equations. I now know the number for each force. So I know the vector. Then I take the vectors and I break them up into x and y components. collect all the x's together, that's my new x. Collect the y's together, that's my new y, and then magnitude and direction. Okay, so we're mixing in equations, physics equations, to get a vector. And then with those vectors, I do this vector math stuff to actually get the final answer. So the sooner we become comfortable calculating components, adding the components together, get my magnitude and direction, once that's comfortable, then all that's left to worry about is, do we know how to use the equation? Because the equation will give us the vector to begin with. So any questions about these vectors?
I have a question. When we're calculating the magnitude of the vectors, can magnitude be negative?
No, it should never be negative. Firstly, because there's a square root there. So if you try to take the square root of a negative number, you're going to get a complex number. It's going to give you an error in your calculator. Secondly, the reason you won't get a negative is because everything inside the square root is squared. So here, notice the negative 8.66, that whole thing is squared. So it's going to become positive when you square it. So even if all your components are a bunch of negative numbers, once you plug them into the magnitude thing, they become squared, so they become positive. So inevitably, your magnitude should always be a positive number. Your direction can be negative, depending on which way it's pointing. And the components can be negative. But the magnitude itself is always positive. It's always, how fast did you go? 35 miles per hour in this direction. You never went negative 35 in that direction. Because if you did, you just say, well, I went 35 in the other direction. So no, you should never get a negative magnitude because everything's squared. So all negatives will turn positive anyway.
Thank you.
Any other questions? Now, I want to make mention, even though I took the whole day to worry about the vector stuff, this semester is not filled with vectors like last semester was. The only topic that talks about vectors is electricity and magnetism. And we're not going to concentrate a great deal on that in this semester. Most of the topics we do won't have vectors. But because it will come up, I wanted to bring it up now so we become comfortable before we start worrying about anything else. Just to review it, because we went over it last semester, whether you had me or someone else, they should have shown it to you. But don't worry, the majority of the class, this isn't the stuff we're doing. Majority of classes, hey, you add this much ice to some hot water, or you put some cans of beer in an ice chest with this much ice. How long or how cold will they get? Or things like this. You're using equations. The vector stuff will be a small part of the semester, but you still need to know it. You still need to be able to do it, because the last thing you want is to know the physical concepts, set everything up, but then not know how to do the math part of it at the end of the day. But don't be afraid that this semester is going to be a vector semester. This last semester was vectors. This semester, not so much, but it'll be around. So hopefully that kind of reminds you about how to do the vector stuff. Of course, we're done for the day. I see it's 1:53. Don't forget, the homework is posted. It's due Sunday, 11:59 p.m. So if you haven't started working on it, go ahead and work on it. You now have all the math review stuff finished. If you do still have some concerns as you're working through it, of course, you're free to email me, and I'll do my best to try to help out. But get that review stuff done, or the homework done, so it's out of your hair. Next week, of course, we'll start into the physics. Thermodynamics is where we're starting. So we'll talk about temperature and calorimetry and things like that first. Also, I need to do the first 2 week census thing for the university. Every semester we have to do this. So I'll probably be posting something on Canvas just as an attendance thing. So everybody, it may be a quiz thing where I just say, hey, type your name. And that way, everybody who's here, whether you showed up today or not, I'll know who has attended the class at least once in this 2 weeks, so that I'll have accurate information to put for the university. So be on the lookout for that. It won't be an actual quiz. It's just going to be some way for me to take an official attendance thing that's on the record, since we're not doing the key cards thing right now. So just be looking for that. And if anything changes, the way I talk is going to be through the email. So make sure you look out for any emails I have. But other than that, if you have no questions for me, you are free to go and enjoy your weekend.
Take care.
Thank you.
Have a good day.
All righty.